Okay. Hello, hello. Hey, everyone. Hi, I'm Ed, organizer here at MLOps London. So welcome if it's your first time. Great to see some new people here and a lot of people who are familiar faces now. It's good to see you back as well. Yeah, thank you all for coming. If you haven't found it already, there's food and drink in there, but it looks like most people have. If you need to sneak out and grab something, just go and do it as the talks happen. This is a meetup. It's all very friendly and informal. The loos are at the back in that kind of sort of invisible door. People ask me that a lot, but it's just through there. There are a bunch of them. And then a couple of things to point out before we get started. So the first one is to thank my company Selden, who help provide this venue and pay for the food and drink, and more importantly, give me time to work on this as a project and bring everyone together to talk about MLOps. So if you're doing like massively distributed training, then Selden is not the company for you, right? We don't do anything in the training space. We don't do kind of data versioning, none of that stuff. Like if you have models that you've already trained and you want to do deployments, that's where we come in. So it's the deploying, the monitoring, the explainability, all of the kind of production level stuff, the kind of day one, day two operations for machine learning. So if that is something you're struggling with, come and chat to me, or I think I have a couple of colleagues around the room as well. So, you might bump into people. And then the second thing to note is that I'd say provisionally, but pretty much locked up now, is that the next date for this will be the 29th of November. So put it in your diaries now if you want to come back. If you don't want to come back, let me know why. I always want to know feedback as well and make these things better and better. So that's, pretty much it for now. I'm going to hand over to Jonas and Paolo, who are engineers from Sky, and they're going to talk about an open source project that they've been working on. And this is really cool because I think, these guys came along to the first meetup that we had, and they were talking about some stuff they were doing. And I said, that's really interesting. It'd be cool if you could talk. And they said, I think they've gone through all sorts of wrestles internally to be able to open source it and then to be able to speak about it. But they are now, here and ready to present. And I think we're all excited to hear what they're going to say about their Kubeflow Pipelines operator. So, thank you. I'll hand over to you two.
Hi, everyone, and thanks, Ed, for the introduction. It's great to be here, by the way. And in many companies, the MLOps journey ends up being more like Romeo and Juliet. But today, we're going to talk about a great love story that has a happy ending. I'm Paolo Ambrosio, and I'm principal engineer at Sky in the personalization space. And I'm here with the other co-author of the KFP Operator.
Yeah, hi, I'm Jonas Mende. Well, it's a pleasure to be here. As Paolo said, I'm a senior software engineer at Sky, working in the personalization space with him. And pretty much we've been working on the KFP operator that we're going to talk a little bit about today for about the last year, really. So what we're going to talk about is the experience that we have gathered working in the MLOps space, and some of the discrepancies that we have found to certain goals, some of the gaps that we have identified, and obviously how we plan to overcome those goals, and hopefully how we have how we plan to overcome those gaps, and how we hopefully have overcome them. Let me see, is that not working? There we go. So what are we going to do today? Well, we're going to talk about a couple of quotes, really, which I'm sure you've either all heard before, or you've made before. We certainly have heard them a couple of times before, whilst working in the MLOps space. And let's start right with the first one. I just need this trained model in production. I'm sure you've all heard this before. So imagine this, right? The data scientist has worked days and nights on a new great model, configured it, trained it, optimized parameters and hyperparameters, and created a model artifact, and now turning around to the machine learning engineers, or to the ops team, operations team, and asking them, can you just put it into production? And then usually what comes is a face like this. And why is that? And the reason why that is, sorry, I'm standing in the picture. The reason why that is really is because this question implies this picture here for MLOps. So let's just step back one step first, discuss what MLOps is for us so that we are all clear and all on the same page, and then we can go forwards. Because that question implies, oh, I have created a machine learning artifact, like a model that I want to give to an ML engineer or operations team, and please just put it into production. Meaning that this implies silos, it implies walls that we hand artifacts over. And really what MLOps is for us is it's about tearing down those walls. It's about breaking those silos and breaking all the collaborators in that space into one empowered team. So empowering the right people to do the right things in a culture of shared responsibility, really. Okay, so coming back to that quote, I just want the trend model in production. What is the problem with that? The problem is you can't just take anything and just put it into production, right? It has never seen the light of day. It has never been tested. It has never been like real customer traffic or anything even remotely to that. So the problem is you put it into production and it might just break. Like with any application that you build, you can't just build it locally, put it in production, and then hope everything is good. It's not how things work. So really where you should be starting on from and where you want to go is you want to have a path to production for anything that you build. And a natural progression for that would be, this is supposed to be development, a natural first step towards that is, okay, let's consider the artifact that I've just built, which is the trained model, and consider that as an artifact that I'm going to promote through the environment, starting from, I have built this in a local development environment, or I have built it in a remote development environment, and then I have this artifact, apply it in development, I sign it off, then I promote it to staging, I sign it off, promote it to production, and then I can run it there. It's a good first step because it covers the problems that we've discussed before. It does not address certain other problems, though, that this approach has. First one is the infamous bus factor, right? So it could happen anytime that the data scientist just leaves the company. What happens is, when the data scientist has trained it on a local machine, well, that machine is lost. All the keys to the remote development environment might be lost as well. And at this point, you have broken continuous training already. You can't train continuously because production will get stale after a while. You will be training a model that will digress over time, meaning that the customer experience will get worse. But assuming that this is solved by having a team where every data scientist in the team is empowered to train it remotely, and then still you're handing it over to an ops team to push it through the stages, then there's still another problem, because all those environments, or basically the platform itself, still follows a path to production. It should follow a path to production, really, because the idea of a path to production is that if things are failing, you want them to fail as early as possible. Ideally in your development environment, but latest in your staging environment, but for sure not in production. So assuming you have an artifact that you can reliably build, but you have a path to production for your platform, and taking that artifact through those, you would basically expect that at any point an environment could break. And at this point, again, your continuous training would be broken because production would get stale and customer experience would digress. What is the next step towards that? Well, to solve that problem, really. We need to take a different look at what artifact we are going to promote through the environment. So far, we have talked about the machine learning model. And now we're starting to look at the machine learning pipeline itself, as in the code that actually trains the data, or that trains the model, takes the data, trains the model, puts out an artifact. That is the artifact that we are going to promote through the various environments, meaning that you have now orthogonal approaches. You have the continuous delivery of the training pipeline, and you have the continuous training of that training in each representative environment, meaning that even if development or staging or both of them should break, you have deployed a working version of the machine learning pipeline training into production, and should new data arrive or on a schedule or on certain KPI triggers, you can retrain. So your continuous training is still happening. Even though something is broken on your continuous delivery path or on your path to production, you can still have continuous training and you can still satisfy customers with the model that you already have.
All right, so at this point, the platform team has listened to all these preachings that Jonas mentioned, and They chose to deploy Kubeflow pipelines in all environments. The data scientists have decided to look at the TFX documentation. They have looked at the quick start. They said, oh yeah, this is quite easy. Let's copy paste this Python code. They deploy regularly the pipelines to all the environments. They have recurring runs that, again, they deploy to Kubeflow pipelines, and everything's working great. They honestly can't understand what the engineers were talking about. This is so simple. And then the platform team upgrades Kubeflow pipelines. DSL changes, and they told them, you need to change all your scripts. And they have dozens of those scripts. So what do they do? This is very common because when we talk about, when we look at the documentation of most machine learning frameworks, there's always this infamous quick start that says, oh yeah, write this Python code and it deploys to your environment. But is that the real thing to do when you're really taking production seriously? We have a mix between machine learning code to describe the machine learning model architecture and something that should be platform specific, like where this train model needs to be pushed for the serving side to serve it, as well as how the entire pipeline gets pushed into the tooling, in this case, Kubeflow pipelines. Wouldn't it be better to have a separation between the two so that the data scientists or machine learning experts just can focus on the machine learning code and everything else is taken, is separate from it? In this case, if they had done this, they could have just copy-pasted the new snippets of code across the entire code base. There would be no mix between machine learning code and deployment, and it would be a lot simpler. But we can take it a step further, maybe, yeah, and we can put those scripts into the continuous delivery system because they don't need to be mixed with the code anymore. So we see that the data scientists can work effectively on the machine learning code, and the platform team can focus on changing those scripts. And there is collaboration between the two because, of course, each needs to be aware of the other, but there is not friction between platform upgrades and machine learning code. So at this point, the final quote we have is, but machine learning is different. And it actually looks like it is. So we have traditional application on one side, where everything is done just by specifying the desired state of resources. For example, to deploy a new version, you just edit a config file, you deploy it saying, I want version 2 from version 1, and there is some tooling that just reflects that into the environment. The developer doesn't need to know how that happens. It could be rolled out progressively. There could be some fancier rollout like canary deployments, but the developer doesn't really need to know. It just says, I want this version deployed to production. So instead, for machine learning pipelines, we have what we call imperative style. So the pipeline is effectively, we need to describe how the pipeline is deployed and how it is applied to Kubeflow pipelines. And it looks like there is no way to fix this. But we do believe that what we are missing is just tooling. And that's why we created the KFP Operator. For traditional application, Kubernetes is the de facto standard now to deploy and manage workloads in an environment. And as I said, it all happens declaratively. So you define the configuration, you define what you want to to be reflected in the environment, and the tooling takes care of it. Tooling, in this case, is Kubernetes. We also have Kubeflow Pipelines that takes care of the continuous training side. We know that once we upload the pipeline to Kubeflow Pipelines and create a recurring run, that model will be trained on a regular basis. What's missing here is something that allows us to define those Kubeflow Pipelines concepts like pipeline, run configuration that are recurring runs, and experiments in a declarative way. In Kubernetes jargon would be using YAML files to describe custom resources. So the KFP operator is the bridge between those two worlds. There is Kubernetes on one side and Kubeflow pipeline on the other side. And the operator also provides some other benefits, like it has an eventing system where we can plug into alerting, or we can trigger a different way of updating the serving side. And it is based on the same technologies that power Kubeflow pipelines. So when you need to install it, you don't need to. It's not going to be a matter of installing a lot of tooling on top of it. This picture is from a paper by Google. It's about the maturity level of MLOps. This is the highest maturity level, level 2. And we can see here how the KFP operator bridges continuous delivery and continuous training that's provided by the Kubeflow pipelines. And we will see in a short demo how that happens.
Okay, great. Let's take a look at what this actually looks like. Because I appreciate that we have been using a lot of engineering terms like declarative and imperative approaches and all those things, which you may or may not be familiar with. So let's take a look at the start of the demo. You will have 2 panels, and I'd like you to think about an analogy first. Think about when you have been in a position where you have been managed by a manager, and think about one kind of manager. Who would be micromanaging, who would tell you on a daily basis what exactly to do, when to do it, where to do it, what to apply and where to apply it to, right? And then at the end of the day, you're just supposed to report back. And then think about the second kind of manager who would just tell you what she wants and when she wants it by, and then she lets you go and execute that, and like giving you the freedom to do that. And now think about, if you ever have been in those 2 situations, which of them was more scalable, which of them better utilize resources of the manager and of the managed person, and which usually yields better results. So put that analogy in the picture here. On the left-hand side, you have the imperative approach, micromanaging a Python script to tell it exactly where to put all, basically, where to put your compiled pipeline. It starts from defining, okay, I have a machine learning workflow. It consists of a couple of steps, really, usually like example gen. In this case, very simple. It's the Penguin pipeline you've probably all seen in TFX. So it's example gen, it's training, and it's evaluation, and then at the end, it's a pusher. So what you're doing is you're mixing 2 things. You're saying, this is my machine learning model, this is what it looks like, this is the data science behind it, and then you tell it exactly, I want the model to be pushed to this location, this remote location, and then I want the compiled pipeline, I want it to be uploaded to this Kubernetes endpoint and all the KFP endpoint, and all those things. And now think about what of those things really are relevant to data scientists on a daily basis. It's probably going to be something like, what does my artificial neural network look like? Or what does my k-mean clustering, what is it parameterized by, and all those things, right? And those are the things you won't be focusing on, and not the boring parts, like where should the model be pushed to, or what is the KFP endpoint, what environment am I training in? Those are concerns that you're usually thinking about later, like on a per environment basis, or that's something that the environment or the platform abstracts away for you. So, imperative style code, let's comment out a couple of things that we don't really need, that we can factor out. So starting with the pusher, there's a bit more down here, which is probably going to be difficult, but I'm going to explain. The pusher, we're just commenting out because, again, this is not a concern of a data scientist, really. It's something purely environmental. It's dependent on the platform. And usually all the models that you are training are going to push to a central directory or central repository anyway. So let the platform do that. Similarly, down here, what you would see, let me take a look at the screen, is, right, the pipeline route would be following next. Sorry for that, we can't really scroll because it's a video. So the pipeline route, so this is really where all the intermediate steps of your pipeline execution on Kubeflow Pipelines would be stored and all those things. Again, platform specific, not really relevant to your artificial neural network. So comment that out as well. And then a couple of other configurations, like the pipeline name can change for environment, or can change on a daily basis. Like it could change because product decides it wants a new name for it. Who knows? So can be configured away. Surely that's usually driven by config anyway, but let's take a further step and just put it into a declarative description on the right-hand side. So if you're familiar with Kubernetes, which I'm sure a lot of you probably are, you will see it's just a configuration file where you tell Kubernetes exactly what you want to apply and where. So imagine you have put this into a Docker container, which you usually would do anyways. You tell Kubernetes exactly what version of the operator you want to deploy it. You tell it what Python function in the container is used to create, well, down here you would be returning the list of the components. And that you tell that there as well. What you would see down here as well, I skipped over that, is you would, before commenting out, there would be a step to actually compile it and upload it to Kubeflow. Not needed anymore. That's done by the operator in the background. So here you just tell it what you want and where you want it, and that's it. This is a very simplified example. You could extend it with like environment variables or execution parameters for things like your execution environment, like beam arcs and things like that. You could all put them in there. And then just treat it like your regular Kubernetes application. So you apply it using kubectl. You've probably used that before. Apply the pipeline YAML in this case, just apply it, and then the Kubernetes, the KFP operator takes care of applying that into the system. So you can see here a live view of what is like the actual state of your resource, which is currently in creating. In the background, the operator takes several steps. For anyone who's really interested, these are Argo workflows. Takes several steps to compile it for you, not happening in the Python code anymore. It uploads it for you, and it also updates it for you as it gives it a proper version on the KFP endpoint. Then, once that is done, the operator takes the resource into succeeded state, and it will then actually, well, give you an ID that you can use and that you can show on the UI as well. So what you have done, what you have achieved at this point is you have declared what pipeline version you want, and you have applied it to the system. So far, so good. Now let's create the same thing for a run configuration. This is how you would usually do programmatically or in the imperative style, micromanaging Python script. You would tell it what project you want it in, you would tell it what region, you would tell it what is the KFP endpoint and all those things, which again, you can put into configuration, but because of all the problems that Paolo has outlined before, really you want it factored away and away from your data science code, right? So let's do that. Let's comment it all out and then just apply a run configuration. In the run configuration, what you'll see is, well, obviously it has a name, but it also points to a pipeline that we've just created, which is the pipeline sample. In this case, it just tracks the latest version of the pipeline that you've just created. You could specify a fixed version as well, and you tell it to train on the fixed schedule. And all the environment specifics, that's abstracted away for you in the configuration of the operator, because again, it's similar to all the models that you're training in the same environment, so why put it into your application code? And then we're going to apply that as well. And the same thing happens. The KFP operator in the background takes care of synchronizing your desired state, as in pipeline sample should be trained on the 23rd minute after the hour, and applies that to the backend of KFP and creates it. And obviously, the next logical step is, well, it was created at, but it should be running at 23. So what's happening next is just creating the run. Obviously, that's not what we built, right? That's Kubeflow. So let's take a step back and let's take a look what has happened here. So we have converted an imperative programmatic style of telling the system exactly what to do in what environment to do it, and we factored that, or we abstracted that bit out of our data science machine learning code and put it into an operator that we just need to configure for the environment. And now suddenly you have a configuration file, or like a declarative configuration that you can apply to any environment, that you can promote, but that you can also configure for each environment. So you have separated those two concerns of, this is my fancy data science model, and this is where I want to deploy it. And this is suddenly how you have bridged that gap between a declarative configuration management system like Kubernetes and Kubeflow Pipelines. Obviously, this is a very simplified example. Again, so if you do want to know more, like the eventing system that Paolo was mentioning before, all the configuration options, all those things, we have open source the tooling. So feel free to reach out on the link. Feel free to reach out or come up to us later. Discussion channels are on the website as well, so do check it out. Thank you.
Great. Yeah, thank you so much, Jonas and Paolo. A reminder to people on the stream, if you you just drop something in the chat and then I'll ask the questions. I'll come back in a second. Yeah, for people in the room, any immediate questions, raise your hand. I'll come around with a mic. If you can speak it through here, that helps so people online can hear what's happening. Amazing.
Hello. It might be like a little bit silly question, but why do you even need to test things and, use your model or train your model with development staging? Because it can be contaminating, can't it?
It can be what, sorry?
Contaminated. It was like dirty data, maybe. Why not just production?
So I hope I got the question right. Basically, let's go back a few slides, and then I can show again like why you would want to have that. So if you take the model as it is and put it into production straight away, like you have trained it anywhere and you want to put it to production, then production might break at any point, right? Because you have never seen it working in any environment. So at this point, you need to put it through lower environments. You need to put it through a promotion procedure, or you need to put it through a testing procedure so that you can verify it actually does what it's supposed to do. Because there could be loads of things wrong. It could be just misconfigured, or like serving might just break down because, for example, you're using different features in your model than you're actually anticipating. Like your production environment, your serving side supplies features to the model that it's not been trained with, and all those things may just break all of a sudden. So you need to put it through that rigorous promotion procedure from one environment to the other, or really any testing procedure, right? Usually would have several environments. Any testing procedure that would ensure that you're not breaking in production. Like before you put it in production, you can't break there.
Yeah, and at this point, in this version of in this diagram, the model is not promoted. So the serving side, yeah, it's unfortunately you can't see here in the room that's serving at the bottom. So the serving side is promoted, the pipeline is promoted, and the continuous training produces a different model in each environment. So the model for production will be trained in production, the model for staging, trained in staging, model for dev will be trained in dev. But we know that as things move from dev to production, we know that things work together as a whole, because otherwise if you train something in development and then you use the serving in production, it might be that the serving in production is not able to serve the model that's been trained in dev. But if everything goes together, then we can have the guarantee that it works across all three environments, or whatever environments you have.
Does that answer the question?
Yeah.
Cool.
Just a follow-up question on that.
And you say it, and I'll repeat it.
So how do you configure your development environment? Because like in most of the companies, you won't have the production-like data in your staging. You don't tend to keep it. So if you are developing your model in your development environment where you don't have the production-like data, how can you expect your model will perform the same in the production, even if it is the same code? And if the strategy is like we will develop it, promote the code, we'll see how the model performs in production, and then do the backtracking, then like take the feedback loop, then very slow feedback loop.
Yeah, so the question was about having like training in dev where we don't have production data, right? And how that, like how can we make sure that the model works, is going to work in production if the data is not there? So this system works when you have also your data structured in a certain way, so that your data pipelines also have a path to production. So you might not have the same data in dev, because each environment will have its own data. Some will have production-like data, all production data. Others will only have synthesized data, maybe. But it's all about the protocols and making sure that it's not about is the model, does the model predict the right, like it's not about the inference, it's about will it break? And about the inference, of course, you have other stages in your training where you can put some validation, you can put other safety nets in place to determine if your model is good enough. Like the validation phase before the model is blessed, it will tell you if it's of good enough quality. And then there is a step that's afterwards, like after the model starts being served, where you need to determine, is this model actually working for our customers? And you can never do that either in offline testing or, like it doesn't matter if you have the production data or not, you still need to take action afterwards. So to make sure, if you make sure that your model actually doesn't break in production, then at least you're going to serve those inferences to customer without breaking production. But you will never know until you see the customer reaction and you measure your KPIs if the model is actually working. I hope that answers your question.
Okay, it answers. But my main concern was like it's a very slow feedback loop.
Well, the feedback loop needs to, like, it's on several levels, right? So this quick feedback loop that we have is about the components working together. And you have slower and slower feedback loop as you go more towards KPIs compared to technical measurements.
And the idea is that you make this feedback loop so mature and so reliable that you can still have a very, very fast, quick feedback loop, but you can do it so often and so quickly that on any change on your model, really, you're pushing it to the same loop. But for that, you have to have the tooling in place so that you have the confidence that this tooling takes it from one level to the other. You don't have to think about it because, again, it's a boring part. It's a very repetitive part that you don't want to do over and over again. Yeah.
Cool. Yeah, I think it's a really good example of how there's a lot in, like, you see in a lot of the literature and news around MLOps at the moment that it's about building ML systems now rather than, like, we're not deploying ML models. And I think that was kind of historically people were like, train a model, that thing is the asset that I promote. And now it's, once you reach a maturity level where you realize you're actually retraining and trying to spot drift and things like that, you have this whole system around it. So how do you build that in a reproducible way? And I think that's what's really cool here is you've shown how you can do that. Quick question from me, and then I don't know, put your hand up if you have one. I'll come to you in a second. I'm just interested in some of the use cases you have at Sky. How many is this used now for all of the machine learning use cases you have? How many models have you got? What types of things are they doing?
Actually, it's not. So this happened in the last year. So 1 year ago, basically, we had close to nothing. We had just started developing this. So it's used only in the personalization and for our recommenders. And so all the machine learning models that power our recommenders do use this tool. We are expanding that to more business areas. where we're going to work with the data scientists to onboard them in this, because they are currently working in the old style of a lot of manual work to deploy every machine learning model. And it is a real pain for the data scientists, because they're usually the one left with like doing that. Like the platform team says, oh yeah, you got this, you got the Airflow, and now you do it. And so we started small in the personalization area, because that's where we work, but we are expanding it to other areas of Sky.
And just to be clear, like for us, this is still the very beginning of the journey. But what we've done is, because we put it on the same footing as other applications, like services, like APIs, it means we can now plug it into other tooling that we use or we can use for advanced rollout scenarios, like A/B testing, multi-arm band, and all those things, right? Can't really have those, or canaries, blue, green, all those things, can't really have this unless you have a certain level of maturity for your rollout procedure. Now that we have that, we have the clouded approach. We can apply that to principles like GitOps, and then suddenly you can plug it into A/B testing and all those things. So that's really an enabler towards those more advanced rollout scenarios, because again, when you talk about serving 25 million customers, when you talk about serving several models, you really can't have manual procedures there anymore. And you really can't have things training and in development and then breaking suddenly. It needs to happen on the production data, on the regular cadence, on a regular schedule, or when KPIs change and all those things. So that's why.
Cool. Okay. Quick question from online here. I mean, it's a bit broad, but can you explain the code? Here's what Kadapa says. I guess maybe, yeah, just at a very high level. Yeah. Maybe from the demo. Yeah, from the demo, that I think. I guess if you're completely unfamiliar with Kubeflow and the pipelines, like what were you showing there?
So I'm supposed to not explain the code of the operator, but of what we shown in the video.
Yeah, I think so.
Okay, cool. There was a very simple model that is straight away taken from the TFX example, Penguin pipeline, which is really just the 3 steps. It's an example gen. In this case, even just gets it from a CSV file. Usually would be plugged in BigQuery or some database right in there, and then it's I can't even remember what the training actually does in this case, and just to train and evaluate. A really simple example, you could put any model there that you want, especially recommendation-based models that you want to train. This part here, I assume that the question is related to what is happening around there, what are the parts that we are commenting out, which is probably more important. So this is the pusher. So if you're unfamiliar with KFP, this is a component in the graph. Can we show the graph? If you scroll to the last couple of frames in the video, where the model is trained, and you will see there's the pusher, right? So yeah, we have example gen, trainer, and then at the very end there's a pusher, and the pusher is the part that actually takes the model artifact and puts it, in this case, into a GCS bucket. Which again, data science related, training an artificial neural network or regression model, I can't remember, and then this is the bit that then takes it into your environments, which is so disconnected from the rest that it really doesn't belong into your data science code. Hope that explains it.
That's great. And any other questions in the room? Okay, brilliant. So yeah, let's have a round of applause for Paolo and Jonas. So we're going to take a quick sort of 5-10 minute break. Go and grab another drink. Do whatever. Right. Take a minute to breathe. I'm going to mic up Laszlo, who's going to come and talk about reducing sort of the kind of technical debt that you get in machine learning projects a lot at the moment. So it should be a really, really good talk. So don't go anywhere, but do go and grab a drink. And there's a little bit of food left as well. So if you're quick, I'll see you in a minute. Okay, welcome back. Firstly, so this is less for people online who can actually see everything perfectly, but for people in the room, apologies for this. There's a panel missing, and you guys have had to use like, well, I don't know, 11% of your imagination tonight to decide what goes in. Maybe we should have got like GPT-3 to generate the text for that section, and see what people's slides end up being filled in with. But yeah, the good thing is on the recording, all of the stuff's there. So if something tonight you were like, oh, I really wish I'd seen the code in that corner, you can go and check it out on the YouTube channel afterwards. Okay, so enough about that. Yeah, final reminder that the next one will be on the 29th of November. It'll be out on the meetup page soon, but you can put it in your diaries now. And then a second kind of call out to anyone who is interested in speaking, even if that sounds really daunting and you're like, oh, I don't think I have anything to talk about. Actually, if you work in machine learning, in DevOps, anything kind of related to that, you always have something interesting to talk about. Whether it's a little bit of small amount of code you did at work that was really exciting and you're proud of. You don't have to stand up and talk for half an hour as well. We could do a 5-minute lightning talk or something like that. So do come and find me if you think you have anything to talk about. I'm always looking for speakers. With that, I will hand over to Laszlo, who some of you I'm sure have seen on MLOps podcasts and webinars and things like that. The sort of guru and consultant. I'll let him talk about himself in a little bit. And he's going to talk to us about reducing technical debt. So yeah, thank you, Laszlo.
Thanks for coming to my talk. Thanks for the Sky guys for the beautiful presentation. I think it's going to line up with your work nicely. Can I have a show of hands who are practicing data scientists in the room, right? And then who are machine learning engineers, MLOps engineers? Everyone else, right? Okay, so let me start my presentation with a quote from 18th century Prussian general von Clausewitz. Machine learning is the continuation of software engineering by other means. We are going to see in this talk that we can, as machine learning engineers and data scientists, we can take a lot from software engineering, who figured this out in the last 30 years, and accelerate our work with their practices. The title of my talk is Clean Architecture, how to structure your ML projects to reduce technical debt. First, we are going to look at how technical debt ruins your productivity, why machine learning products are particularly prone to gather technical debt, and then we are going to talk about a couple of simple software engineering concepts to help yourself. Because this is an MLOps meetup and most of the audience is a machine learning engineer, I would like to say that this talk is preliminary written for data scientists who are working with MLOps in productionized environment. So what are they need to focus on, how to work together better with MLOps people. About me, so my background is in finance. I used to work in mobile gaming as well, and I was head of data science at the London fintech, where we worked with industrial scale natural language processing for investment banks and hedge funds. Most of the content of this talk is coming from experience from there. We are consultants in the last 2 years since COVID, and we worked on this concept since then, and we teach data scientists to write better code in our free time. I have a blog, Laszlo, L-A-S-Z-L-O, and substack.com. The missing part of the slides can be downloaded. I have a blog post there with the slides. Please download it and subscribe if you would like to have more of these contents. Let's take a look first of what do we mean by machine learning products. We don't treat machine learning operations as part of the product. It's an infrastructure where machine learning products are appearing as users. So we try to use these infrastructures as part of our project, but the ML product is usually a business-facing problem. And it's also not data analysis. What's the difference between a product and an analysis? An analysis starts with a request from a stakeholder, you execute it, and at the end, you hand over the insight back to the executor, and that limits the life cycle of an analysis. While as opposed, an MLOps product is usually there is some kind of complex business process. It is described by end-to-end input-output relationships, not rules. Why not rules? Because if it's rules, then why would the machine learning engineers turn up? The software engineers would have already solved that with rule-based systems. Why do you take away they bread? These are expected to work autonomously, not completely. So sometimes you have like active learning and human-in-the-loop systems where you can interact, but generally they have some kind of independence from human interaction, and it has a long lifespan. And this is a very important concept because it means that if you are improving, if you invest into the quality of the machine learning product that has a very long time to yield, and the ROI can be very high even in small invested increments. So why does technical debt matter in machine learning products? Products are usually dealing with fuzzy real-world business problems. As we said before, these are usually really complicated, a lot of ad hoc rules, usually a lot of human interactions, which makes them hard to describe. This makes them inherently unspecifiable. What does it mean? It means that no matter how careful you are in specifying a machine learning product, you are going to end up finding things that you have forgotten while it is already in production. So what do you need to do? You need to go back and edit and change your product, which means that you need some kind of capability of change. This is usually described as agility, and technical debt is usually described as a lack of agility, inability to change. And not only they are inherently unspecifiable, they require constant updates because the business context changes, the environment changes where you are working, and in general, the situation is just fluid in these situations, and you need to solve these problems by changing your machine learning product. And obviously, if you have too much technical debt, you're not going to be able to do these changes. You're going to have problems. Let's take a look at the ML lifecycle as we usually think about it and how they are contributing to technical debt. And I think this is particularly lines up with the Sky presentation, which we've seen before. Usually, you think of it as 5 steps. You have first an EDA when you are dealing with the data. And in the POC phase, you are worried about the model. The MVP stage, you are worried about productionization, so you're getting it into production. And in the A/B testing, you are worried about fine-tuning, and BAU is concerned about monitoring. So what is the problem here? Obviously, usually the first 2 steps are done by different teams or different people than the second 3. It means that the data scientists are creating the models, but everything else in production will going to be left with the MLOps teams or the MLE teams. And the problem is that you are gathering user feedback at the last 3 stages. It means that any kind of insights will going to come from these places, which needs to be shoveled back to the beginning of the pipeline, so the data scientists can incorporate into the assumptions of their models, and then they need to hand it over again to the machine learning team so these new insights can be turned into production as well. Clearly, this is as friction. If you have a friction in your deployment pipeline or in the integration pipeline, it means that you're doing it less and less, which means that changes are going to accumulate, which means that every new deployment will going to be a bigger deal, which means that, you know where I'm going. It means that you are creating a larger and larger business risk, which means that the testing will going to be more heavier, and sooner or later you start thinking in terms of versions, and in later, most machine learning products are not actually updated, they are actually rewritten from scratch because there's no point trying to update the previous structures, so much technical debt arrived. So what's the difference between technical debt and technical mess? Technical debt is not lack of specification, documentation, or infrastructure. These are just administrative tools around this, and infrastructure is just a component that you are using as part of your product. It's also not missing features. If you haven't finished your product, you are just not at the end of your roadmap. Just go through this. That's not technical debt, and it's also not broken models. You have bias or drift in your product. You just need to train a new model. That's not technical debt in itself. And the one which is missing from here, I'm just going to read it for you. It's not bad practice. Bad practice is technical mess. If you are not executing your daily job at a certain level, you are not creating technical debt. It's not a catch-all phrase where you can get away with things. You are just creating technical mess, which needs to be cleaned up before you can talk about technical debt. So what is technical debt? Technical debt is an attempt to gain knowledge with a plan to correct it later. So it means that when you are making a conscious decisions to go into one direction, you need to be able to immediately know how you are going to get back to the state where you are going to undo this. If you don't have that, you're having technical mess. I'd like to quote Ward Cunningham, who was the person who quoted or coined the term technical debt. Paying back technical debt depends on writing code clean enough to be refactored. Obviously, we see that, to talk about technical debt, you already need to be at a certain level. But what does it mean to refactor something? So what is refactoring? So refactoring is changing the code without changing its behavior. Why would you change the behavior of the code if you have already written it? We all know that there are multiple ways to write and to solve the same problem in computing, and there is no reason that the first version you wrote is the right version. So it means that once you solve the problem, you need to move on by refactoring it, by rewriting it in a way that is more suitable for a production environment or for your plans. It requires two things. The first is fast testing. There is no refactoring without testing. If you change your code, you need to verify that you haven't changed its behavior. This needs to happen. Otherwise, you are going to do it rarely. And again, you are going to be in friction, and you are going to not having the right continuous integration pipeline. And it also requires what's called experimental operational symmetry, or EOS for short. Let's take a look at what experimental operational symmetry. It's a fancy name by Google for running the same code everywhere. So you're running the same code on your laptop in testing, training, evaluation, and production. This enables refactoring. So what does it mean to change the code and not changing behavior? You are changing the behavior of the code in production. And you need, while you are working on your laptop, a way to verify that you are not going to break your production code everywhere. Obviously, you can't make it sure ever. And this is why you have staging deployment and retesting in different environments. But the core concept is there. And it requires decoupling. What does decoupling mean? It means that you reduce the dependence of the components of your system. You hide the implementation details behind interfaces. If you have these interfaces in your system, then it means that you can't depend on details of how those are implemented. And that is a key aspect of creating the structure that is necessary for refactoring and removing technical debt. This also helps removing cake, which is changing anything changes everything, which is a particularly bad aspect of machine learning code. If you are able to maintain clear architecture and decouple yourself from these environments, then at least you are able to maintain some part of this. Oh, that's not going to work. I'm just going to get out of this. Is it better?
Yeah, I think we can see most.
Good. Okay, so decoupling is done through two major concepts, which is inversion of control and dependency injection. So what are these? Inversion of control is your code is an abstract entity. You can see this. So the blue box is your machine learning product. This contains the model, the pre-processing steps, the post-processing steps. If you want to define your product as part of the training and the evaluation, then those as well. But obviously, you can have any kind of nuances here. Usually, it's defined as a Python class. Instead of it calling the components of the infrastructure calls your product at the main entry point. So it instantiates your product, and then it calls the main entry points. And your product doesn't connect directly to external resources either, only through adapter classes. What's the point of this? Obviously, your code is not aware of any kind of infrastructure dependencies of your environment where you want to use it. Therefore, you can run it on your notebook, and you can also run it in production, the same code. And this is how you achieve EOS. So, for example, in a test setup, your test harness will going to instantiate your product with the adapters that are present in the environment where you want to execute it, and then the same code is going to run, and it doesn't know that it is being tested. It behaves exactly the same as it would happen in production, and this is the key aspect of decoupling and EOS. So how does it look? A bit more detailed view on. Just going to go back to. So how does it look in production? Usually when a data science team starts working on a machine learning problem, then they would like to focus all their effort in the business problem or the domain problem itself. And this is why the business problem is in the middle. This is surrounded by business problem related aspects of the task, like domain model, which is describing of what kind of entities the business process is dealing with, the business logic into which your model is going to be entered, and the models themselves. And only this is surrounded by the classic aspects of machine learning, like data sets, feature engineering, and model training. And only these aspects of the system we're going to connect to the infrastructure, the databases, and storages. So it means that your business problem, the part where you spend most of your time, will not going to be dependent on the environment. In a test environment, only the outest perimeter, the infrastructure, and the most concrete elements need to be replaced, and the rest is the same. Therefore, you don't need to worry about that you are evaluating your code in a staging or a production environment or your laptop. You can have the same features, and you can run the same code. We are going to look at three major design patterns that are helping you to implement the decoupling. So these are decoupling from various aspects of a system. So the adapter pattern allows you to decouple from external services. The factory pattern allows you to decouple from data sources, and the strategy pattern allows you to decouple from algorithmic decisions. This is a particularly important pattern for machine learning because a significant portion of your work is spent on trying various techniques. This is where you solve problems like executing efficiency, where, for example, you solve a problem with an inefficient but clearly readable way, and then you replace it with a highly efficient one, and you compare the differences between them locally. Okay, this is one again. I'm going to. Is it good? This? It's good. Okay, so let's take a look. Can you read it actually?
Read it back?
Yeah. I see someone nodding at the very back. Thank you. So what is an adapter pattern? So let's take a look. This is like a very, very simple machine learning product. It's just already been refactored to be defined as a class and the entire infrastructure is just a Python script in line 17, which is instantiating this main class and then calling the main entry point. What happens in the main entry point, a connection to a database is created, and the simple query is run and collecting some data frame from it. What's the problem with this? Clearly, if you don't have this database at your local testing environment, you are not going to be able to run this code. So this code is not going to be tested. You're not going to be able to refactor this code. Why? Because you need a database to run it. You can see it on the right. What can be a solution? The first step is to wrap any kind of database-related code with a specific class. And in the main function, you only have one line. The main function only knows that it's going to get a source, and the source have a get data entry point, and it's going to return a data frame. And any kind of database-related code is going to happen in the adapter class. Why is it working? Because you can take the instantiation in the main infrastructure. You can see that you can replace the main class and instantiate the adapter there and run it as it is. But for example, in a test environment, you can replace this source with, let's say, getting the data from a file. All right, so let's take a look at the next one, which is the factory pattern. So I can actually put it here. Right, so the left-hand side is the same code that we see before, which is a the refactored version with an adapter to a database. But the problem here is that the adapter is returning a solution-specific format. It is returning you a data frame. If you want to solve a business problem, you're not having data frames. You have like some kind of entity classes. What you can say in the right-hand side, you're clearly saying from the query, you're getting back customers. You can refactor that you have a data class, and you are getting these customer classes back. So it means that your business problem became more business-like. You are not dealing with data frames, but you are dealing with actual classes that have some kind of meaning in your work, right? So let's take a look at the last one, which is strategy pattern. Essentially, what you do, for example, here in the main class, you are creating a logistic regression, do some kind of transformation, and then return a prediction into the rest of the main function. What's the problem with here? Obviously, if you want to try another model, you need to rewrite this class. And instead of that, you can wrap any kind of model-related code into its own class, self-contain the transform function as well, and then the main function only get an instantiated version of this model, this wrapper, and then call this in a non-specific way. Someone says that this is just like you're treating the algorithm itself as an external resource, which is a quite fitting analogy. And you're also getting an extra benefit of using this pattern, what's called coherence. Let's take a look at, for example, in this solution, you are using a deep model which has like multiple layers, and this layer, the fact that it has layers, it is passed through several places in the constructor and to a private property, and then passed to the deep model at construction time. What's the problem here? Obviously, if you want to use a model that doesn't use layers, but let's say you want to swap to a random forest which has trees, what do? You need to rewrite this entire code just because you swapped one model to another, and everyone needs to kind of know the inside details of creating this model. So what can you do? Obviously, you can, if you have the model extracted into its own class, you only that particular point needs to know about that it has layers, and you can remove this code from the main part, and you made your code more coherent because only the minimum set of people or entities know about a particular detail of the code. All right. I'm going to put it back. I'm just going to keep this. So how does a workflow in this structure start from scratch. When you start a project, obviously it can be daunting when someone tells you that you just need to maintain code quality throughout the project. People usually freak out from this. But where do you start? So usually you define your data classes. You usually have some kind of business problem. They have some kind of representation in the database. During the EDA phase, you define your data classes. And wherever you're getting these data classes, you wrap them with adapters, with factories. So they are creating these data classes, which immediately makes you independent of these data sources. Usually you set up a test environment, or very simple idea locally is to test on 0.1% of your real data set. Just run a test run, and that is going to pick up any kind of typos or errors that are obvious. And then obviously in a staging environment, you increase this percentage to the real data set, and obviously 100% evaluations are production grade tasks, but can also take days or even more. The next step, you define your interfaces. Obviously, so you have the factory pattern, the test environment, and you set up your interfaces. Any kind of things you want to do. That's usually the verbs. And then start collecting these interfaces into service classes, because everything eventually needs to be turned into a class. You just wrap these together as you feel. And then because of you have the test environment, you have the refactoring capability, it's easy to think this way, because it means that you can change your decisions anytime. You don't need to worry about changing your own code. Then you start structuring with dependency injection. You start replacing parts and putting them at the right place. Any kind of external services in a production environment will going to be wrapped with adapters. And then you can set up the production environment. But as I said, you are moving the same code that you did in the test environment, just replace the adapters at the places. Obviously, if you find out that something doesn't work, you need to refactor it, but the refactoring is a natural exercise. And the last one is you create experiments with a strategy pattern. If you created this product and it works somehow in production, but realize that some aspect needs to be changed, like a feature engineering part, you want to use a different model or an ensemble, or models are related to each other, then you can start experimenting with a strategy pattern. You can run it in test environment, and then you can put through this cascade, and the end, the same code will going to be deployed into production. The next one is, obviously, all data scientists work in Jupyter Notebook, so it's not possible to avoid that. But how do you work in notebooks and still maintain this this environment? Don't forget that all of your what you are concerned about, the data classes, are created by factories. You can instantiate these factories in your notebook and then get this data into data, and then turn them into data frames for analysis. So the analysis happening in notebooks through the helps of factories. And you can create custom experiments by instantiating your main program in a Jupyter Notebook dependent environment. Because your main program is just a class, you can create one, and then you can pretend that you are in production and then call it or run a large-scale evaluation. And because of the strategy pattern, and you can refactor it, you can plug in these and then run experiments in Notebook without actually setting up an environment. So what are the benefits of this workflow? You have good layers of abstraction. This is what we find. You do notebooks for analysis. You write your VS Code, your product in VS Code. You import it back into notebooks, and then you have this mindset, and it works very well. You can outsource the infrastructure parts, the writing adapters. How this is going to get into production. You can outsource this. Obviously, if you work for a startup, that's usually you on a different day. But obviously, if you work for a larger organization, then probably it's more helpful. But it is a very good collaboration tool, because it means that you are speaking the same language and you can help each other. That's one of the biggest problems what I see in data science workflows is, there's a bit of a fight going on between people doesn't like to work to each other. That allows you to a collaboration. You define interfaces, and then how do you move on from one side to another? It's up to negotiation. You have a high level of flexibility. You can experiment without without destroying your previous versions. So this is one of the biggest problems in data science workflows, that often you're worried that you change your code and you're never going to be able to go back, because every code, what you think of as production, and your output is version controlled in a way that is tested. You can change it, and if you break something, then you can just go back. There are managed complexities. So what does it mean? It means that often what you say is complex problems need complex solutions. Sometimes you say is like, we solve complex problems with simpler solutions, but that's usually not the case. What you want to do is manage this complexity. And because of the decoupling, a bounded context, and the separation of concern, these are helping you to always concern on one problem and then extract everything else outside. EOS enables you to push and change straight into production, and this allows you to high-speed iteration, which is the most critical part of machine learning. I do think that EOS is a critical feature of any kind of production-grade machine learning system. It means that the data scientists themselves write the code that is going to go into production. Okay, so some takeaways as the last slide. So machine learning is inherently unspecifiable. Therefore, technical debt is inevitable. It's going to happen partly because you are unable to figure out what's going to happen in the future. The only way to remove technical debt is refactoring. You can't refactor without testing an EOS. If you want EOS, you need decoupling. And decoupling can happen through clean architecture, and you can use inversion of control and dependency injection to solve these problems. And the first step to start on this journey is to learn what adapter, factory, and strategy patterns are. And thank you very much for your time. And my blog is at laszlo.substack.com. You can download the slides from there, and there are a lot of other content around this. Thank you very much.
Great. Thank you so much, Laszlo. I'll go into the room and do questions again as we did last time. And if people on the stream have something, stick it in the chat and I'll come back to it. So yeah, any questions for Laszlo? Cool.
Simple one. How do you make sure your code is scalable?
What does scalable mean?
Can pass from 10 users or 1,000 users to millions of users?
That's a very good question, because usually data scientists are not concerned about that, because in a distributed system, the MLOps engineers are a problem by instantiating multiple versions. But because your code is a abstract service, you can see an object as a service, you can create multiple of them if it's parallelizable, and this problem is solved by them. You can argue that what other problems can happen in scalability. Large-scale evaluation, that's a major problem because it means that the data needs to be fed from multiple sources. But because your code is abstract, you can create an infrastructure that creates multiple of these and parallelizes this problem for you.
Great. Anyone else? Yeah.
How do you convince data scientists that is their problem and not someone else's?
That's a good thing that I have an Eastern European accent. I can shout louder. Yeah, that's a very good question, and we spent huge amount of energy on that, and especially on the resistance. This talk is part of a long series of talk which we do as training, and the first part is the psychology of agile processes and why those are better. Why do you feel better? Because clearly data scientists are very frustrated, software engineers are frustrated, like data scientists are an order of magnitude more frustrated why they are doing the job. And it's like, this is the coolest job in the world. It's like, how come no one likes it? And if you look at, and this is part of the problem here, here, the handover. you think of the handover, there is a psychological concept called self-determination theory, which has 3 aspects: autonomy, mastery, and relatedness. What does autonomy mean? It means that I can do whatever I want, right? I solve my problems however you want, right? I'm not micromanaged, as you guys mentioned. Mastery means that while I'm doing it, I'm getting better at it, right? So I mean that I have a higher yield tomorrow than today, so it's worth practicing. And the third is relatedness. I make an impact, right? So what happens here when you are handing over your model to the machine learning team? The data scientists have no impact on the customer. They are getting feedback through a feedback loop from the machine learning engineers, and they are incredibly difficult to impact anything in production because they're waiting for you. So what does the machine learning engineers do? They have no say on what goes into production because that's a data scientist problem, right? It means that you manage to cut both autonomy, both mastery, and both relatedness in one go. It means that if you have these 3 components, if you don't have these 3 components, even one missing, you are going to stop doing what you're doing. Or you're going to be frustrated doing it because the only reason why you're doing it is because you're getting paid. And this is one of the reasons. So this is what we usually say. And then focus on all aspects of how your mastery will going to grow, how your autonomy will going to grow when we are going to do that, and how we are going to be more related to the solution and the success together. And it creates a collaborative environment. But you do need to do this, like have a reason, because they are going to say, I'm not going to do this. It actually doesn't matter whether you are going to be about twice to 10x faster with this than otherwise, because they're just not going to believe you.
Great. Anyone else in the room? Or should I'll go and check the chat on the stream quickly. A question from me whilst I do that. So particularly the kind of approach you showed with adapters and factories and so on, there are quite a lot of tools out there that can make that part easy for you. Do you have any particular favorites or...
Do you have an example?
I don't know. I'm thinking immediately of something like ZenML that kind of abstracts some of those things from
it's
you.
Usually, so ZenML is an infrastructure component, and usually as a data scientist, and this is one of the primary aspects of clear architecture, is you're not making any kind of infrastructure decisions until the last minute. It means that the data scientist can focus on the business problem until they absolutely must deal with some kind of infrastructure problem. And this is usually happens at a later stage. They're still shipping their own code, but at that point, they're going to have like feature requests is saying that, let's say this part of the code, like a feature store, for example. What do you do now? You have an MLOps stack, and then you need to make a decision that I'm going to have this feature store now. It doesn't matter whether you need it or not for your machine learning products. You can't avoid this decision because that's how MLOps stacks are built. But here in a clear architecture, the data scientists can take their code to the last minute, and they can just wrap a feature store in an adapter and treat it as an external resource and get the information from there in production environment. And this is how this enables you to be more flexible, because often we work with companies who doesn't have any kind of MLOps infrastructure, which means that you can't really suggest them to buy this and that, because we don't know whether we are going to need it in 6 months' time when these things go into production.
Okay, yeah, thanks. There's a question here on the chat that says, hang on, I understand you usually like to persist data in gzip files. Do you also persist train and test sets, or do you think that data splitting should be in memory and or specific to a model service class? Should I repeat that? That was quite a lot. It's a very long sentence.
Okay. No, it's okay. I'm actually thinking. Yes. So it's if I understand, the question is, like, how do you store data? And I think it's an important aspect that I don't say I don't care, but it should not matter for a data scientist where the data is coming from. It should come from an adapter which spits out data classes. And if you have this situation, then you are in a good situation, because someone else can make the decision. Maybe that's a data scientist as well. And indeed, we use gzips usually and JSONs to store this data, and not data frames or pickles. but it doesn't mean that's the right solution. It can come from a database, and the adapter will going to convert it for you to some kind of domain-specific work, and your code only depends on domain-specific code.
Okay, and then I think if I'm just kind of breaking that down again, having reread it 3 times, there was a probably asking about best practices on like test, train, split type things. So the question kind of was around: should you persist those or do them like in memory, right? And then you might get different splits each time.
Yeah, you should. No, it doesn't matter. Like this is an optionality whether it makes sense or not. So, for example, we usually work in natural language processing where you have hundreds of gigabytes of text data. We don't persist those. What we do is we have a deterministic splitter which is not randomized, and we simply read the entire file in and just throw away the parts which are failed in the test set. But we are still at lineage because we know if in the future, if we decide whether something was part of the data set or not, we have a deterministic way to figure this out. And I do think that these are feature questions which needs to be implemented in ad hoc in the current situation.
Great. All right. Well, what we'll do is we'll wrap up there with a quick round of applause again for Laszlo. Thank you very much.
Thank you very much.
And this is the bit where kind of everyone wins, right? If you're on the stream, you're already home, so there's no commute. And if you're here in the room, you can hang out with people, network. There are hopefully still some drinks kicking around. Come find the speakers if you had other questions you were too embarrassed to ask. Looking forward to catching up with you all. And we'll see you next time on the 29th of November. Thanks.